Good morning, dear students. Today we shall see the coordinate systems used in finite element method. In finite element method, we use three types of coordinate systems. They are global coordinate system, local coordinate system, and a natural coordinate system. So when we use the global coordinate system, we use the global coordinates to specify the points in the entire structure. We use the global coordinates to specify the points in the entire structure. For example, I take a structure like this. It is a truss structure. It is a truss structure. Observe this structure carefully. This is a truss. One end is fixed. Other end is supported on a roller like this. Other end is supported on a roller like this. Right? It contains several truss members. This is truss member 1. Observe carefully, these are the joints. These are the joints. This is truss element 2, truss element 3, 4, 5, 6, 7, 8, 9. This is a two-dimensional truss structure. Right? To define any point in this truss structure, we want two coordinates. Two coordinates. To define the geometry of the domain, you want two coordinates. So therefore, to define the entire geometry, we consider the global coordinate system with coordinates, say x and y. X and y are the Cartesian coordinates. Right? To specify this point, you want how many coordinates? Two coordinates. The first coordinate is x1 and the second coordinate is y. So y1 is 0 here. So what are the coordinates therefore? x1 and 0. These are the coordinates of this point. If you want the coordinates of this point, how many coordinates you want? Two coordinates. Say x2, y2. To specify this point, I want two coordinates. Say x2, y2. The first coordinate is x2 and y2 coordinate is 0 because this point is lying on the coordinate axis x. Right? Now to specify this point, we want two coordinates. Say x and y. What is the x coordinate? This is the x coordinate equal to x1. And what is the y coordinate? This is the y coordinate. So therefore, you can write x1 comma and the distance of this point from x-axis. Okay? This I say, say y3. This is how you can specify all the points of this structure by the help of a single coordinate system. OXY. Right? We use the same coordinate system to specify all points in the structure. Such a coordinate system, what is called global coordinate system. So we take, a member here, right? This is a one-dimensional bar, an axially loaded bar, an axially loaded bar. The bar may be subjected to a tensile force or the compressive force. I take a bar of uniform cross section. It is axially loaded. To load it axially, I keep one end fixed At the other end, I apply the force F. So here, cross section is same throughout. To specify a point in this domain, I want only one coordinate. Therefore, I can consider this as one-dimensional problem. The properties of the material, the geometry of the domain and other dependent parameters are dependent on only one coordinate x. Therefore, I can handle this as one-dimensional problem. Now, if you discretize this member, right, into finite elements, I have 3 elements here. Say 1, 2 and 3 finite elements are there. What are the nodes? This is node 1, this is node 2, this is node 3 and this is node 4. So how do you represent this? You can represent this domain like this. Okay? So here I have taken only 3 elements. I have taken only 2 elements, not 3 elements. Right? It is a 2 element, 3 node model. Now, to specify the node 1, you want only one coordinate, that is x1. That is x1. This is the coordinate origin. This is the direction of x-axis. To specify the point 1, you want the coordinate x1. To specify the point 2, you want the coordinate x2. To specify the point 3, you want the coordinate x3. x3. Distance of node 3 from the coordinate origin. So here all the points are specified with the aid of a single coordinate system. Right? Therefore it is a global coordinate system. Understand? The coordinate system used to define the points in the entire structure is the global coordinate system. Now, observe this. As I said, this is a truss structure. Right? How many elements we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 elements we have. To define the geometry of this truss structure, we have considered a global coordinate system OXY. Any point on this structure you can specify with the help of 2 coordinates x and y. Right? Now, local coordinates. Local coordinates are used to specify a point on the element in the structure. The structure consists of several elements. Here we have 12 elements. If you want to specify a point on the element of the structure, you have to use local coordinates. Local coordinates are used to derive element properties, whereas global coordinates are used to derive the properties of the domain. Local coordinates are used to derive element properties of the subdomain. When you assemble all the properties of the subdomains, you get global properties. They are the properties of the domain. So global coordinates we use to derive global properties or properties of the domain. See here we have again a truss structure. We have again a truss structure. If you want the properties of each element, For each element you have to choose a local reference frame. You want the local coordinates, therefore. I have element number 1 here, truss element 1. Truss element is a two-force member. Truss element is a two-force member. It is a member of uniform cross-section. It is a member of uniform cross-section. It may support either compressive forces or it may support tensile forces. Tensile forces. Whether the forces are compressive or tensile, their magnitudes are equal. And they are the collinear. Both forces have the same line of action. Understand? Whether they are compressive forces or tensile forces, both forces are collinear in action. In truss member, either compression takes place or tension takes place. Truss member is a two-force member. Truss member does not undergo bending because the forces are collinear in action. They do not constitute any moment. Why? Their magnitudes are also same. Right? Truss member is subjected to two equal and opposite forces. They are collinear in action. Hence, the truss member is not subjected to bending. Either compression or tension takes place. Right? Now, to define a point on this truss element 1, you want a local reference frame. You want a reference frame with local coordinates. Which means that each element possesses its own reference frame. For each element you have to take a separate reference frame that we see. This is the truss element 1. Right? The truss element 1 connects two nodes, say 1 and 2. Say 1 and 2. Okay? This is the orientation of truss element. Each element has different orientation. Right? Now, for this element, you can take x-axis like this and y-axis like this with coordinate origin here. Okay. Because for each element we take a difference frame, a different reference frame. Right? I use the coordinates like this. For element 1, say x1 and y1. x1, y1 are the local coordinates for element 1. Right? Or you can say x dash, y dash. Doesn't matter. X dash, y dash are the local coordinates for element 1. Right? Next. This is second element. See here. This is second element. It connects two nodes. See 1 and 6. Second element. This element has a separate reference frame. A reference frame with local coordinates, say x1. For the whole domain, if you take a reference frame, for the whole domain, if you take a reference frame, OXY, OXY, like this, because the element 2 is on the x coordinate axis, the same reference frame OXY becomes the local coordinate system, the local reference frame to element 2. Once again I repeat, because the whole domain, the domain of the entire structure is defined by the reference frame OXY. The same reference frame becomes the local reference frame to the element 2, because 2 is lying on the coordinate axis X. That is what we see here. This is element 2 which connects two nodes 1 and 6. Right? For this element we have a reference frame OX. In fact, OXY is the global coordinate system. The same global coordinate system we can consider here for this element as the local coordinate system. So both become same because element 2 lies on coordinate axis X. Now, element 3, it is vertical in position. It connects two nodes, say 2 and 6. Right? For this element, we have a local reference frame like this. X dash, Y dash. X dash, Y dash. Where the element 3 is, say here. Element 3 is here, vertical in position. For this element separately, we have a local reference frame like this. Do you take like this with X, Y dash axis leftward and X dash axis right upward? Yes, you can. Otherwise, you can take with X dash axis upward and Y dash axis rightward you can take. I draw here. Same element I take. Element number 3. This is node 6. This is node 2. You can take Y dash axis rightward if you want. And X dash axis up. Or you may say, I take X dash axis rightward and Y dash axis upward. Yes, you can have your own reference frame, your own local reference frame for this element. Again, I take like this. This is element 3. This is node 2. This is node 6. I take X dash axis like this and Y dash axis like this. Each element must have a separate local reference frame. That is what we have to understand. Okay? For element 4, I take local reference frame like this. So when we consider the local coordinates to specify the points on the elements of the structure. Next, natural coordinates are very, very important. The system of natural coordinates permits specification of point within the element. They are considered as local coordinates. To specify a point within the element, we can use natural coordinates. Natural coordinates. Using local coordinates also we can specify a point on the element. How we specify a point on the element using local coordinates? We can also use natural coordinates to specify a point on the element. Therefore, natural coordinates can be considered as local coordinates. Natural coordinates represent dimensionless numbers. They do not possess units. They represent dimensionless numbers. They represent unitless quantities. Next, they never exceed unity. They never exceed unity. The values of natural coordinates never exceed unity. Next, how they are obtained? The natural coordinates are obtained by assigning weightages to the nodal coordinates. Weightages to the nodal coordinates. Right? So now, the system has the property such that if the coordinate at node I is unity, it is 0 at other nodes. That we see when we derive the natural coordinates. Okay? The use of natural coordinates is observed in assembling the element properties for global properties. You can use the natural coordinates for preparing the element properties, and the element properties are assembled for global properties. Now we shall see the natural coordinates in one dimension. I said natural coordinates represent dimensionless numbers. They never exceed unity. They are used to specify a point within the element. They are used to prepare element properties. Okay? Now, we take a one-dimensional member. What is the example? A bar of uniform cross-section. May be loaded in tension or compression. A bar of uniform cross-section. Right? A one-dimensional bar we take. Okay. So now, this is node 1, this is node 2. Where x is the global coordinate axis. Where is the origin here? O is the origin. The node 1 is specified by the coordinate x1. Node 1 is distant x1 units from O. Next, node 2 is distant x2 units from the coordinate origin O. Okay. So therefore, length of this member is simply x2 minus x1. That is L. Length of this member equals to x2 minus x1. That is what we can observe. Okay. Now, I take a point, say P, on the element between the ends, which is specified by the coordinate x. Because it is one-dimensional problem, we want only one coordinate to specify a point on the domain. That is x. Point P is distant x units from O. X units from O. Okay? Now, tell me with respect to point 1, node 1, what is the distance of x? It is simply x minus x1. Therefore, this is. What is the distance of x with respect to x2? Now, it is simply x2 minus x, which is this. x2 minus x, which is this. Okay? Now, as I said, natural coordinates are determined giving weightages to the global coordinates. You have to impose weights to the global coordinates. What is the global coordinate here? X. Therefore, L1 x1 plus L2 x2 equal to x. That is one expression you get. Another one is sum of the natural coordinates is unity. Therefore, L1 plus L2 equals to 1. We have two unknowns here. What are they? L1 and L2. They are the natural coordinates. They are the derived coordinates. Right? Natural coordinate never exceeds unity. If L1 is unity, L2 is 0. That is what I said. If the value of natural coordinate at one node is unity, it is 0 at the other node because sum of the natural coordinates is unity. Sum of the natural coordinates is unity. Come here. If L1 is unity at node 1, L2 is 0 at node 2. If L2 is unity at node 2, L1 is 0 at node 1. Right? Sum of the natural coordinates is unity. Okay? Now, L1 plus L2 equals to 1. Now, L1 x1 plus L2 x2 equals to x. We have two equations with two unknowns. Now, these two equations we can represent in matrix form. Right? A 2 by 2 matrix having elements 1 and 1 in first row, x1 and x2 in second row into a column matrix having the elements L1 and L2 equal to a column matrix having the elements 1 and x. If you expand, you get like this. 1 into L1 plus 1 into L2 equal to 1. First equation. Next, x1 into L1 plus x2 into L2 equal to x. Second equation you get. So these two equations are represented in matrix. Now, what I want the natural coordinates L1 and L2. Okay. Now L1 and L2 which equals to inverse of this matrix into this. Inverse of a 2 by 2 matrix having elements 1 and 1 in first row, x1 and x2 in second row into a column matrix having the elements 1 and x. Now, a column matrix with the elements L1 and L2 equal to, now, inverse of this 2 by 2 matrix. Inverse of this 2 by 2 matrix. How you get? 1 by x2 minus x1 into transpose of a matrix having the elements x2 minus x1 minus 1 1 into a column matrix having the elements 1 and x. Right? I hope you know how to determine inverse of this matrix. Now, a column matrix having the elements L1 and L2 equal to 1 by x2 minus x1 into transpose of this. Right? So when you write the transpose of this, what happens? In the resulting matrix, row becomes column. So therefore, the row of elements x2 and minus x1 becomes a column. x2 and minus x1. This row of elements becomes a column, minus 1 and 1 into a column matrix with elements 1 and x. This equals to 1 by x2 minus x1 into, multiply these two. Then what you get? x2 into 1. x2 minus 1 into x minus x. Next, minus x1 into 1 minus x1 plus 1 into x plus x. Right? Next, a column matrix having the elements L1 and L2 equal to, how you get? A column matrix having the elements x2 minus x by L and x minus x1 by L. What are L1 and L2? They are the natural coordinates. I said natural coordinates represent dimensionless numbers. They do not carry units. We check here, right? If you take a member like this with uniform cross section, okay, with nodes 1 and 2, okay. Now to define every point on this member, you can take a reference frame like this with coordinate axis x and origin here, for example, the node 1 is specified by the coordinate x1 and node 2 is specified by the coordinate x2. Now I take node 1. At node 1, x equals to x1. Right? L1 I take. At node 1, L1 equals to x2 minus x1 by L. What is x2 minus x? x2 minus x is simply length of the element. Therefore, at node 1, L1 equals to x2 minus, what is x? x1 divided by L. x2 minus x1 is L. And L by L, this equals to 1. That is what we understand. At same node, L2, this equals. Now, x minus x1. At same node, x equals to x1. Therefore, x1 minus x1 by L. This is 0. At any point, if you sum up the natural coordinates, the summation is unity. 1 plus 0 equals to 1. Now, take node 2. At node 2, determine L1. L1 equals to, at node 2, x equal to x2. So therefore, x2 minus x2 divided by L, it is 0. At same node, L2, which equals to, what is x? x2. x2 minus x1 divided by L, which equals to. Again at node 2, L1 is 0, L2 is unity. When you sum up these two natural coordinates, the sum is unity. So from this we can understand that at any point on the element, the sum of the natural coordinates is unity. Okay? Next. And one more thing is, at node 1, L1 is unity. And at other node, L1 is 0. L1 is unity at node 1. And L2 is unity at node 2. Another observation. At every point on the element, sum of the natural coordinates is unity. If L1 is unity, L2 is 0 at every point. If L2 is unity, L1 is 0 at every point. Sum of the natural coordinates is unity. If L1 is 1 by 2 at any point, at the same point, L2 is 1 by 2. Right? Because natural coordinates never exceed unity. Do you observe any case where L1 is greater than 1? No. Right? Next one. If L1 is unity at node 1, if L1 is unity at node 1, L1 is 0 at node 2. If L2 is unity at node 2, L2 is 0 at node 1. Observe these diagrams. These variations you can see here. This is a member connecting say 2 nodes, or you can take an element, finite element connecting 2 nodes. Right? Variation of L1, natural coordinate L1 with respect to length. L1 is unity at node 1, it is 0 at node 2. Next, variation of L2. L2 is 0 at node 1 and unity at node 2. Okay? Observe here carefully with respect to both the diagrams. L1 is unity at node 1 and it is 0, and L2 is 0 at the same node. L2 is 0. L1 is 0 at node 2 and L2 is unity at node. Right? Thank you. Thank you very much.